Hello everyone and welcome to lecture. Today we'll be talking about integration of both scalar and vector fields and different ways of doing this. It might be a good idea for you to review some concepts from previous calculus courses. Specifically the concepts of double integration, which is taking the definite integral of a function of two variables over some domain, and of triple integration, which is taking the triple integral of a function of three variables over some domain in 3D. Be a good idea to review some of these concepts from a previous multivariable calculus course, because we will be using these as we go through and define some of the things that we'll be talking about when it comes to integrating both scalar and vector fields. So the main thing that we're going to start with is what's called the concept of line integration, or the line integral. And put quite clearly and simply, this is the integral of a scalar function or scalar field over a curve. This is the we'll kind of the breaking off point for this lecture, where we'll kind of start and kind of introduce how to do this, and we'll actually see some examples of special types of line integrals that are used for actually giving us information about vector fields. So we can use line integrals to investigate both scalar fields and vector fields, but we'll start by just introducing this concept of line integration. So to begin with, let's assume that we have some curve, a parametric curve in 3D in general, and all of the formulas will derive, and the methods we will derive will be able to be applied in a certain way to any number of dimensions, so 2D, 3D, and you can even extend some of the ideas to higher dimensional spaces. But we'll start by assuming we have some curve in three-dimensional space. So the curve comes up like this, and then maybe loops around, maybe continues up like this. And we've seen how to define a curve in terms of its parameterization. We can parameterize the curve in general in terms of some parameter t, and where t maybe ranges from a to b. Let's say we have some point here on the curve. We'll call it our starting point. It'll be r. Let's say we go to some other point on the curve, and we'll call the ending point that we're going to go to Q. So the starting point R here, we can think of as the parametric curve, this over right here. There's if it's parameterized, it's the parametric curve at the parameter A, and this point right here is the position vector at B. And every single point along this curve is parameterized by this parameter t. We know that we can also write this in terms of arc length if we want to, where the parameterization of this curve in terms of arc length is just going to be starting at 0 at r of a right here, and the arc length varies all the way up until we get to the final arc length, which is the total length of this curve from r to q right here. And we actually know how to find the arc length as well through the integral that we talked about before. And it turns out that the integral that we introduced before, we've already kind of seen a line integral in some sense. We've seen the most basic line integral that defines arc length. So let's assume that this curve is in 3D, in three-dimensional space, and maybe it's immersed in some scalar field, right, that we'll call phi. So phi of r is some scalar field, and maybe this is a scalar field that has a relatively high value up here, and then as we move away from this region right here, the scalar field maybe goes to a lower value, illustrated by these orange points right here. And it continues to decrease maybe as we move away from this region in 3D. And so I guess these green points we can think of as where the scalar field is at kind of like a medium value. And then it's even at a lower value over here, say. To the point where we get far enough away, we're at maybe some blue value. And these colors are indicating the value of the scalar field at each one of these points. So what we're going to consider is how to find the accumulation of this scalar field on this curve itself. And the idea here is that, on this region of the curve, the scalar field is whatever this light blue value is, and then it increases as the curve moves through space it goes through the green region, where this corresponds to the value of the scalar field. Then on this region of the curve right here, the value of the scalar field is yellow, until it moves up into this region right here, where the value of the scalar field is orange, red. And similarly, in this region right here, the scalar field is taking on the green value. So this function could be a number of different density functions, right? A nice way of thinking of phi is thinking of it as like some sort of density function along the curve. Could be a mass density function or a charge density function, but we'll see that this is the best way and the correct physical way of actually determining the mass of, say, a wire, if you have a distributed mass along the wire. So let's kind of remember that this wire is in this field. It could be a potential field. It could be like the gravitational potential field. It could also be, say, like a mass density field or a charge density field. But we're going to kind of consider taking away just this this color right here, so that we have a nice sort of picture of our curve as it's immersed in the mass density field. And this might give us kind of a better picture of exactly what we mean by phi here being defined on the curve. So the function phi is a function of three variables, x, y, and z. So it's a function of position. But really, the line integral is just focused on the integral of this scalar function on this curve, so restricted to this curve right here. And the idea here now is going to be the following. So we have this curve defined and this scalar function defined. The scalar function is defined, it's scalar field, so it's defined everywhere. But really we just want to think of what's the accumulation of this function on this curve from A to B. And this is the main idea of what a line integral is going to be telling us. The notation for this, and we'll see why this is notation, is the following. We say that the line integral over the curve C of phi of r with respect to S, where S is arc length here. This is the notation for the line integral. And just like for the integral of a scalar function of a single variable, we want this to mean something very specific. It's going to mean the accumulation of the scalar function phi on the curve C. And so let's go through and see how to define this. And what I'll do is I'll draw another little picture of the curve here, just so I don't have all of this color on the curve, and it's a little bit less flashy. So we have our curve starting at R here, going all the way to up and kind of looping around and ending right here at some point Q. This is our curve C. So what we consider is called, we consider a partition of the parameter space. So we consider a partition of the interval from A to B, where this partition we can write a number of different ways, but we'll just call it BT. We start at A, what we call that T0, T0, to T1, T2, T3, so on and so forth, all the way up to Tn minus 1, Tn, which is equal to B, the end point of this interval. And this is important. This partition is an ordered partition, right? It's an ordered list of values of t, and we have that the width of any element of this partition, or any the distance between any two values here, we can call delta ti, for I from 1 all the way up to n. That's just going to be ti minus 1. And this should be familiar if you remember your concept of Riemann sums from a Calculus 2 class, or an integral calculus class. But the idea here now is that this sequence of values, t0 to b, actually corresponds in three-dimensional space to a list of points. R of t0, which is R of a, which is the starting point of this curve. Then you have here R of t1, R of t2, and so on and so forth, all the way up to R, position at tn minus 1, the final point on the partition, which is R of tn, or R of b. So what we're doing when we partition the parameter space is we're cutting this curve up into a whole bunch of pieces, where each one of these pieces right here, say like this piece right here, this is R, the position at ti for some value ti in our partition. This position right here is R of a, or R of t0. This position right here is R of b, or R of tn. But in general, the more points that we have in our partition, the finer this partition is going to be, and the finer this mesh is. So the idea here is the following, right? This is R of ti, this is R of ti minus 1, the previous point in the partition here. An approximation to this distance right here, this is the actual distance along the curve right here, an approximation to this distance is going to be, if we just consider the difference of this vector and this vector. So here in this picture, if we draw a straight line here, and we'll call this delta Ri. In general, this is a position vector. That represents this line right here. It's a distinct directional, ordered line. R at point ti in the partition minus R at point ti minus 1. But this is kind of going to be the key idea here in defining this accumulation. What we're going to do is define what's called a Riemann sum. You'll remember that from your Calculus 2 class. But this Riemann sum now is going to be an approximation of the accumulation of a scalar function along this curve right here. So you'll remember that the best way for doing this is going to be in terms of this approximation right here. So for a lot of points in our partition, the length of delta Ri is going to approximate delta Si, where delta Si is the change in arc length along this curve. So you'll remember this from before. So we'll kind of try to show this a little bit more clearly here. So let's set up a sum that approximates what we're going to call the accumulation of the scalar function phi on the curve C. This sum is going to look like the following. I'll call it Sn, be the summation from I equals 1 to n of the scalar function value phi at some point along the curve, pi we'll call it, times delta Si, where delta Si we're defining as delta Si, is this exact length right here, the magnitude of delta Ri, or the magnitude of this vector right here. So this vector, this summation, is in some sense an approximation of points on the curve, where each one of these points pi is a sample point at some point along the curve in each one of these subpartitions. Like this could be like P1, P2, P3, and so on and so forth, all at every single one of these subintervals. So we're evaluating this scalar function on the curve at some point on the curve, and we're multiplying that by the infinitesimal length of it's the approximate arc length, which is the length of each one of these lines right here. So this summation makes sense as an approximation to the accumulation for a number of different reasons. Right? For instance, if phi of r is a linear mass density, or we'll say that more specifically, we'll say it's like a 1D mass density, so a mass per unit length along the curve. Then this summation is saying that an approximation to the total mass you get by taking the mass density at each one of these points, each one of these partition points, or some specific sample point inside the partition, and multiplying it by the total, an approximation to the length in each one of these subintervals. And we would expect this approximation to get better and better and better as the number of points in our partition gets more and more and more. So this is exactly a good way of thinking about this summation right here. So we're really kind of thinking of this in direct analogy to the Riemann sum from a typical integral calculus class. So first things first, what is exactly delta Si? And we've said that delta Si is the magnitude of this difference vector right here. This the difference between r at ti at this point right here and r at ti minus 1. It's the length of that vector. So this is exactly equal to the square root of delta xi squared plus delta yi squared plus delta zi squared. So this Riemann sum approximation is like saying the summation from I equals 1 to n of phi at pi times the square root of delta xi squared plus delta yi squared plus delta zi squared. And this is where one of the very nice theorems from single variable calculus actually comes in, and this is called the mean value theorem, or MVT. Right, so we know that x is a function of t, y is a function of t, and z is a function of t. So under suitable assumptions on each one of these functions, we can apply what's called the mean value theorem, which says that in any interval, in any interval from, in this case, t to t plus delta ti, in all of these subintervals, we have that x at ti plus delta ti minus x at ti. Remember, this is the same thing as delta xi. This will be equal to the derivative of x at some special point ci, we'll call it, multiplied by the length of the interval, delta ti. And this same thing happens for y of t and z of t as well. So delta yi is going to equal to x, or y prime, the y derivative, at some point ti. The mean value theorem guarantees the existence of this point di, the existence of this point ci right here, and then delta zi will be equal to z prime, the z derivative of the t derivative of z, at some point ei times delta ti. So this is guaranteed to us by the mean value theorem. So under certain relatively nice assumptions on the functions x, y, and z, which are always going to be true for a nice piecewise smooth parametric curve. Any piecewise smooth parametric curve will obey these assumptions. So what's nice then is that this expression for Sn, which is we're going to be seeing as we've already seen, is a nice approximation to the total accumulation. This is going to be equal to the sum from I equals 1 to n of phi at some sample point pi times, when we plug in the mean value theorem results, we get x prime at ci times delta ti squared plus y prime at ti times delta ti squared plus z prime at ei times delta ti squared, the square root of this entire thing, which we can simplify. We can factor out delta ti squared to get that the Riemann sum approximation becomes the summation from I equals 1 to n of phi at pi times the square root of x prime of ci squared plus y prime of di squared plus z prime of ei squared, all times delta t I or Sn is equal to the summation from I equals 1 to n, and this pi we'll just say is some point intermediary. So it's phi of the position r, say ti star is this point pi to give us a t here, and then this becomes, this is equal to the square root of it's an approximation to the velocity. It's very similar, looking very similar to the velocity, only this is only these, in general, these CIs, these DIs, CI, DI, and EI are different values of the parameter t. So this is not the velocity, but we're going to see very quickly that this doesn't really matter, because what we're interested in is the limit as the partition gets smaller and smaller and smaller, right? So when we define the partition, we define the delta ti as the change in the partition. We can go through and actually define what's called the infinity norm of the partition, which is the maximum over all I of the absolute value of delta ti. Right, so it's the maximum size of the partition, and what we're interested in is the limit of this expression as this the maximum size of the partition goes to 0, because we've already seen this is a nice approximation to the accumulation of the field phi, the scalar field phi, along the curve, right? And the idea is that we're interested in the limit as this partition gets smaller and smaller and smaller. So as we sort of cut this up into smaller and smaller subpartitions, right? We want to look at the limit of this summation right here, just as in the case of with normal Riemann sums from an integral calculus course. And it turns out that when we do this and we take this limit, we get exactly the definition of the line integral. So it turns out that the line integral along the curve C of the scalar field phi of S ds is equal to this limit. It's the limit as, well, n goes to infinity and the maximum partition size goes to 0 of this Sn. It's the approximating sum. And not only that, what's nice about this this formula up here is that this gives us an explicit way of writing down, a way of computing this line integral. In terms of the parameter t, it's exactly the definite integral from a to b of the scalar field at phi of r of t. So the scalar field at each point along the curve. It's coming from this term right here. And this exactly is converging to the magnitude of the velocity vector field at every point. And then this becomes a differential, or dt, in the limit as the partition gets smaller and smaller and smaller. So this formula is probably the most important formula that you're going to want to remember initially for line integrals, that the line integral of a contour along a contour is exactly equal to the definite integral from a to b of the scalar field at r of t times the magnitude of the velocity vector of that curve along c times dt. So with this integral, the integral of this function with respect to t, and this is actually kind of really nice because we didn't even use it in the definition of this this equation when we're getting this definition. But remember that ds dt is the arc length with respect to time, and we showed that this is equal to the magnitude of r prime of t. Really, I mean, if you remember, what we're seeing right now is that the arc length is just the line integral of the scalar function 1, the constant function 1. Because when we do this, the constant function 1, so you'll recall from arc length, we already showed that the arc length along any curve is just the integral from a to b, if it's parameterized by t, of 1 times the magnitude of the tangent vector dt. This is how we defined arc length. So line integral is just a generalization, like I said before, of the arc length integral. It's a very nice generalization because it allows us to do a lot of different things. We'll be able to understand vector fields better, and we'll be able to understand how to find the accumulation of scalar density functions along curves. There are many different things that we can do, but the idea is that this is the correct notation for a line integral now. Other notations that you might see that are common and that I might use are the integral along c of just phi ds. We won't denote the arc length dependence. We'll just write this. This means the same thing as this right here. You might see the integral along c of phi of p to denote that we're taking points on the curve c, and we're evaluating the integral of the function phi at p ds. Right, these are notations that essentially mean the exact same thing. But what we should do is summarize some basic properties and some more basic notation as well, because we're going to be using these line integrals a lot. I know the name's called line integral, but it's really the integral along a curve, right? It's the first thing that you want to think of. So the first thing, this is just some notation right here. We have some more notation. So if C is a closed curve, then the endpoints match up. Right? It means R at A is equal to R of B, which means those two endpoints coincide or match up. Probably write coincide here. R of A is equal to R of B. Or the other, I think we use Q and R for our points. That means Q is equal to R. These points are the same thing on that curve that I drew before. This is called a closed curve, and these are going to be really important. But we have the following notation for a closed curve. The line integral around a closed curve. If C is a closed curve, we put the integral sign, then we make a circle here. This just denotes that C is a closed curve, and you still just write of phi ds. And evaluation is still the same, right? It's still going to be evaluated exactly the same way as it would have been evaluated if it was an open curve. Just for a closed curve, the two endpoints coincide. And it turns out that this line integral along a closed curve has a very important relation to what's called path independence of a vector field, which we'll see is also very closely related to whether a vector field is irrotational or conservative. And it's very heavily related to those other theorems that we were talking about in the previous lecture. So this is it for some basic notation. And I just want to describe some basic properties of the line integral before we start getting into actually, doing maybe some examples. So very, very similar properties to the normal single variable integral, and to double integrals and triple integrals as well. The line integral over C. I'm not going to go through and prove these, but I recommend that you should go through and check these. By check, I mean prove. You should use the definition to prove these. So you should use the definition to prove these. Right. You'll see that a lot of these are gonna, when you go through and do that, they come directly from corresponding properties for the single variable integral, because ultimately the line integral of a function is defined in terms of the single variable integral. So a lot of these properties are really going to be straightforward and coming directly from the fact that we proved these properties, hopefully, or you've seen the proofs for these properties in an earlier integral calculus course for integrals of this form. So the first property is that the line integral of a constant times a function will always be equal to the line integral of the function multiplied by the constant. Sometimes called the constant multiple property. You also have the sum property. It's linear under constant multiples, and it's linear under a summation. If you say do the line integral of phi of r plus psi of r, where these are two scalar functions, this is going to be equal to the line integral of the first function plus the line integral of the second function. These two properties make the line integral a linear operation. Just like any other integration operation that we have, it makes it a linear operation. One that is also similar to before. You remember, if you take an integral and you integrate the integral in the reverse order, you reverse the sign of that integration. There's a property that's exactly, in some sense, the same. You have that the line integral over a curve C of some function phi of r ds will always be equal to negative the line integral on negative C of phi of r ds. And it does take a little bit of explanation here to define what this notation means, but it's not too bad. It makes it very, very intuitive. We just mean negative C is the same curve as C, but traced in the opposite direction. So far these properties should be looking relatively familiar to you if you've ever taken a course in integral calculus, and then also in multivariable calculus as well, because you remember that a lot of these properties, all of these properties really, in some way or another, generalize to double integrals and triple integrals from a multivariable calculus course as well. So you're going to want to remember that when you're going through doing computations. It's very, very important. So the next property that we have to generalize, properties here continue. Is called the additivity property. And this property has to do with if you have the line integral on two separate curves. So this is saying, let's say we have, I'll draw a picture here to kind of make this a little bit more clear. Let's say we have some curve C1 and some curve C2. Well, mathematically, we call the combination of the curves C1 and C2. So we consider tracing out over C1, and we just pass, and we also include C2 in this blue curve right here. We call this blue curve C1 union C2. Mathematically, this is the union, or the mathematical union of these points. So this is the notation that we use for that. But this is the additivity property says that the line integral along C, where C is the union of two curves C1 and C2 of some function phi of ds, and I guess it is important to, I mean, you can omit the functional dependence on R here, but you really want to remember that phi is always a function of position R. So the function of R ds in this line integral is now going to be equal to the sum of the line integral over C1 of phi plus the line integral over C2 of phi. And this is super important for us because many of our curves are going to be piecewise defined curves, and we're going to need to use this additivity property in a number of different ways. This is sometimes called additivity. So this will be a good summary of all of the main properties that we have for line integrals. And now let's kind of see this in action for an example. Let's consider that we have the following problem that we want to solve. So suppose that we have a wire, a helical wire, with a mass density along the wire. So this is going to be mass per unit length along the wire. So along the length of the wire that is quadratically varying with distance from the origin. question. What is the total mass of the wire? So this is the question that we want to answer. And this is a great example because it kind of takes an idea directly from physics and is giving us a direct example of where this line integral comes up and why it's really important physically to understand our interpretation of the line integral. But by the way, I also want to point out that this example could be word for word replaced with an example from electromagnetism. We are asking for the total charge of the wire. And honestly, if you wherever else you could come up with an example where you have a density function or some function of something per unit length, right? You could use that as an example here. So it's a very, very important idea. But so first things first, we'll say that phi of r is the mass density, or the 1D mass density along the wire. Right, so this is measured in mass per unit length because it's mass per unit length along the wire. So phi of r here is going to be some constant d. This constant d just guarantees that the units will work out correctly, times x squared plus y squared plus z squared. So here I put quadratically varying or quadratically proportional with distance from the origin. So in this case, we know that x squared plus y squared plus z squared is the same thing as the length of r, or distance from the origin, squared. It's the magnitude of this vector. So this gives us exactly what was asked in the question. Specifically, we're asked for a quadratically varying mass density that's quadratically varying with distance from the origin. What is the mass of the helix? So this is our density function for this problem. And then the curve that we want to parameterize here is the helix. And we'll make this simple on ourselves. We'll just consider a helix. We won't consider the rate of rotation. We'll just consider the helix. It is rather general, or general enough for our purposes. The helix with a radius of r, and then a growth rate in the z direction of a. You'll remember that this was the correct way to parameterize the helix. And we'll also say that we just do this over one turn of the helix, or for t from 0 to 2 pi. Because you could go over multiple turns, and we'll see that that's as easy as changing the bounds of integration in our line integral. So we'll just do one turn though, so from 0 to 2 pi. So before we even go through to calculate the integral, we're going to want to go through and remember our nice formula for the line integral of a scalar function. They're going to involve integrating with respect to the parameter t. We're going to need to calculate the magnitude of r prime of t, where r prime of t is the tangent vector to the curve. So let's do that first. And we remember for the helix, it was a relatively nice result that we got. That this is going to be negative r cosine of t, or sine of t. It's the derivative. We r cosine of t. And the third component is just a. And so the magnitude of r prime of t becomes the square root of this squared plus this squared plus this squared. And I'll let you go through the simplification again if you don't remember, but this ends up simplifying to just the square root of r squared plus a squared. So very nice because this is constant. We also see in this integral, this definite integral, that we have phi of r of t, or the value of this scalar function along the curve, at every point on the curve. So we need to figure out what that is, and this is going to be phi of r of t is d times x of t squared plus y of t squared plus z of t squared, which when we plug in x of t, y of t, and z of t, I'm hoping you can see that exactly r squared cosine squared plus r squared sine squared plus a squared t squared. So phi of r of t is just d times r squared plus a squared times t squared when we go through and simplify this. These are always, when you're evaluating a line integral of a scalar function, the things you want to do before you even go through and do the line integral. Because now, evaluating the line integral over c is easy. And this is exactly, because phi is a mass density function, the total mass is going to be the line integral over c of this mass density function. And so this is the integral from 0 to 2 pi of phi of r of t times the magnitude of r prime of t dt. So the total mass then is going to be equal to the integral from 0 to 2 pi of d times r squared plus a squared t squared times r prime of t magnitude, which just is the constant square root of r squared plus a squared dt. And now this becomes an integral that we can go through and directly evaluate. Right? This simplifies to the mass is equal to d times the square root of r squared plus a squared times the integral from 0 to 2 pi of r squared plus a squared times t squared dt, which is d times the square root of r squared plus a squared times the integral, well, this antiderivative of this function is going to be r squared is constant, so it's r squared times t plus the antiderivative of t squared, which is going to be t cubed over 3. That's going to be a squared times t cubed over 3 from 2 pi to 0. So the total mass then is equal to d times the square root of r squared plus a squared times r squared times 2 pi plus a squared over 3 times 2 pi cubed. Which we can simplify a little bit to a nice final formula. It'll be d times the square root of r squared plus a squared times, and I'll put 2 pi at the very beginning because it's part of a constant, and factor out of 2 pi here to get 2 pi, so d times 2 pi times this times r squared plus and what's left over when you factor out the 2 pi here is going to be 2 pi squared, so it'll be 4/3 a squared times pi squared. And this is the formula for the mass of any helix, right, of any radius r, of any growth rate along ZA. This formula will give you the correct mass of the helix with a special density function. It's a density function that varies quadratically with distance from the origin and you can use this formula over any number of terms that you want. You just have to change the bounds of integration. So if you want to go on, one turn or one full turn and a half, you'd have to go from 0 to 3 pi here, so on and so forth. But the idea here is we can get kind of a nice picture of this if we open up Python and kind of do a quick plot in Python to see this. So if we open up our Python window and run the code, not this code, that's for a little bit later on. This right here is a picture of the helix with, and I'll show you the parameters. It's the helix with the parameters of the curve equal to 1, so a radius of 1, and then an a value of 1/2 pi. That's what this is showing right here. And you see that for this case, the mass density starts at the lowest point of the helix. The mass density is 1 kilogram per meter. And then as you move along the helix, the density grows quadratically with distance from the origin. Right? It grows all the way up to a maximum mass density of 2 at the very top of the helix. And it's at intermediate values. The density along the helix is at different values for every single one of these colors right here. Alright, so we've just calculated a formula using the line integral to give us the mass of such a helix. So for any values of the parameters, we can go through and calculate that. So for example, if we were to open this up, alright, let's just kind of do this specific example that is plotted for us so we can kind of simplify this. For the example plotted, we have that r, the radius is 1, and a is 1/2 pi, and d in the example is just 1, and the units of d are a little bit important. I mentioned earlier that d is just a constant to make the units work out nice. This density function has to have units of kilograms per meters, or kilogram per meter, because it's a 1D mass density along the wire. So therefore, this d right here has to have units of kilograms over meters cubed, because you're multiplying it by the square of a distance. So we'll say it has to be, we'll say units of, for instance, mass. We'll say kilograms per meters cubed. We'll make this work out nicely. And again, if you want to, this is going to be measured in meters, and then A is measured in. It's just a constant. So that has to this has to be units of distance. So if the parameter say is time along the hill, it could be angle as well, but I guess angle is probably better. So we'll use, in this case, a is a rate per angle because we're using t as an angle, radians. So maybe we should use theta here instead of t, but t works just as well. So a is, at a rate, and it's measured in distance per angle. Okay, so this A right here is kind of like maybe meters per radian, and that just describes the growth rate along Z with respect to angle. It's kind of like a little lesson in dimensional analysis here, but the idea here is that when we go through and plug these values into this formula, we'll get the exact correct value of the mass. So this is going to be 1 times 2 pi times the square root of 1 squared plus 1 over 2 pi squared times 1 squared plus 4/3 times 1 over 2 pi squared times pi squared. You get a super nice simplification. And this is going to be 2 pi times the square root of 1 plus 1 over 4 pi squared times 1. And you have here 4 over 2 squared is going to be 1. You have pi squared over pi squared, which is also 1. So this is just 1/3. And what we're left with is that the total mass is equal to 8/3 pi times the square root of 1 plus 1 over 4 pi squared. And this is in kilograms. Or it's approximately equal to, when we approximate this, about 8.48 kilograms. And it's important to note that if you go through and actually use the Riemann sums that we talked about earlier to approximate this accumulation, you get something that's very, very close, right? So the Python approximation of this value ends up being about 8.49. So this is from the Riemann Sum Approximation that we talked about earlier. So the not far off from the exact value, which is really nice. And it also shows that for complicated integrals, sometimes numerical methods are the way to go. Numerical approximations of the integral is definitely the way to go. Well, good. So this is this will be the end of this example right here, and what we want to move into a little bit is the idea of how to investigate a vector field, the behavior of a vector field, with this concept of the line integral. And this is going to be a specific idea. It's right. So using the line integral with a vector field F. And sometimes some sources don't distinguish the line integral of a vector field and the line integral of a scalar field. I think it's really, really important to distinguish between the two, because in some sense, in a very real sense, as we're going to see, the line integral of a vector field is going to be kind of defined using the line integral of a scalar field. So, right, it's important here that we kind of mention that this function phi that we're talking about and we're integrating is a function, it's a scalar function from three-dimensional space to R. It's valued in the real numbers. Just want to kind of mention that, and then here we're going to move into defining the line integral of a vector field, right, where f is a vector field. So it's a mapping from three-dimensional space into three-dimensional space. So the question is, how can we do this? And the main idea is to think of, well, suppose we have a direction field, u. Suppose we have a direction vector defined on every, the unit direction vector defined on every point of the curve C. And we want to measure the total effect of the vector field on C in the direction of u hat, where u hat of t is a unit vector that points in a specified direction at every point along the curve. So it's important to kind of think in terms of pictures with regards to what's going on here. So we're in 3D, we have some curve, and this curve is immersed in some vector field. It could be a fluid flow field, it could be an electromagnetic field, it could be a number of different vector fields. But what we're saying is that we have some direction vector u hat. The black vectors here are the f at r, and the blue vectors here are some vector u hat, which could change. It could be a different point in a different direction at any given point along this curve. But suppose we want to figure out the total or the net effect of the vector field f on the curve C in the direction of u of t. Well, we know that at one point, at any given point t, the way that we do this is through the projection vector. Right? We do the projection of f of t in the direction of u hat of t, which is equal to the dot product, and it's really just the magnitude of this projection is what we care about. So we recall that the projection vector is the dot product of f, so it's f dot u hat times u hat. Right, this will give you that f dot u hat is just going to be the length of the vector field f cosine theta, where theta is the angle between u hat and f. This gives you whether the projection's positive or negative, and it really just gives you the component of f in the direction of u hat. But remember, f here is a function of t, and u hat is also a function of t. So we kind of stumbled upon inadvertently, right, what we mean by this, the way of getting the total effect of the vector field f on the curve c in the direction of u of t. It's to take the line integral of this projection, right? Because we know that the line integral of f, the line integral of phi of s ds over c is the accumulation or net buildup of phi on the curve c, and specifically if we consider the line integral over c of f dot u hat ds, or in terms of our actual bounds, the integral from a to b of the vector field f of r of t dot product with u hat of t times the magnitude of r prime of t dt. All right, this component right here, this is saying take the accumulation of f dot u hat, or the total accumulation or net accumulation of the component of f in the direction of u hat along the curve c. All right, so this is really a measure of just like the net action of a vector field f in the direction of the unit vectors u hat along this curve. Now this is an important idea in its own right, but it becomes very, very special when we consider special values that u hat of t could take. So special directions that we might want to just consider. So we'll consider first, and this is going to be a really, really big idea here. So consider the special direction where u hat of t is the tangent vector to the curve. Remember, the tangent vector of the curve is the derivative of the position vector along the curve over the magnitude of the derivative, or in terms of just arc length, is just dr ds. Right, this is one of the things that we showed. So if we consider this special direction, what we actually end up getting is, and this is in many sources just called the line integral. So when a lot of sources talk about the line integral, by default they're talking about this. This is the line integral of a vector field. Now, I just showed you that we can have more complicated, more different types of line integrals of a vector field depending on what u hat is, but many sources call the line integral of a vector field, they just straight up define it as this integral. So it's the accumulator, it's the integral of the line integral over c of the vector field f, depends on r, dotted with t hat on the curve ds. So it's the line integral of this scalar function. This is sometimes called the line integral of the vector field. And the reason why this is important, and all these notations are important, we'll see in a second, that this is the same thing exactly mathematically, because t hat is dr ds. A better notation for this, and the notation that's more often used, is the line integral of f of r dot dr, or just f dot dr for short. These are just some common notations for the line integral of the vector field f. And really what this is giving you is it's giving you a measurement of the net accumulation of the vector field f dot t hat, or the net accumulation of the vector field acting tangent to C. You could think of it in kind of like a rotating sense. And the net accumulation or effect of the vector field rotating in the direction of the curve. If this value, right, is positive, right, so if it's positive, that means that in general, right, f generally goes with C. If it's less than 0, then more often than not, f goes against C. And if it's equal to 0, then f goes equally with and against. So that it kind of balances out. Direction. So this is a very useful tool, and we're going to see that it's a super useful tool for many different applications. Another very common notation that you'll see for the line integral is it uses the fact that f is typically we denote it as PQR. Right, so this is coming from this notation right here. You could write this as the line integral over C of P dx plus Q dy plus C dz, where you remember that dr we'll write as r prime of t dt. Right? But dr is really just the vector. You can think of it as like dx, dy, dz, the differential. So this is another very nice notation, and I guess the last notation that we want to see, and I want to show, and it's really not notation, but it's how you would go about evaluating one of these line integrals. You can evaluate it using either this notation right here or this notation right here. The idea is this is saying that the line integral over C of f dot dr is the same thing as f of the position vector on the curve as a function of the parameter t. And we'll actually use the original formula right here, because this is the line integral that we know how to evaluate right now. But all of these notations are equivalent and mean this exact same thing. This is f of r of t dot the unit tangent vector, which is r prime of t divided by the magnitude of r prime of t. And then with respect to ds, which is really just the magnitude of r prime of t dt. And you see what's a magic cancellation here. So we're seeing that to evaluate any line integral, all it takes is to take the integral of f at r of t, and then take the dot product with r prime of t, whatever that is, and just integrate that dot product with respect to t. So in some sense, it's actually a little bit easier to take than the line integral of the general scalar field, because it's a very special combination, and it doesn't involve taking the magnitude. All you have to do is take the derivative. But this is the best formula to remember if you want to remember exactly how to get the actual value and compute the value of a given line integral with respect to a vector field. All of these notations that I've drawn down are equivalent to this, right? They mean the exact same thing. But probably the most common that you'll see for a line integral is this notation right here. But this really is coming directly from this idea, the idea of accumulation of the vector field tangent to a given curve. And that's why this right here is the way of evaluating it. Even this notation makes sense, right? If we go through and we have a curve that's parameterized, and you want to view it in terms of this notation right here, which is sometimes easier, right? This dot product is the same thing as the integral from a to b of p of r of t times x prime of t dt plus the integral from a to b of q of r of t times y prime of t dt plus the integral from a to b of r of t r of t times z prime of t dt, right? So if sometimes evaluating these three integrals is easier to evaluate than this dot product integral right here, but the point is that this is what you're going through and doing, right? And it's why this notation makes a lot of sense. So we'll see in some examples, right, how to kind of use this, and how one of the most important concepts, right, that we're gonna be able to consider is the concept of what's called being path independent. Right, so this is going to be one of the huge ideas that is going to be very, very important to us. And the reason this is going to be super important for us is because we'll see that path independence is directly sort of related to this idea of a conservative vector field. And most line integrals are path dependent. They depend on what path you take to evaluate them. But we'll see that a very special class of line integrals is path independent. So we'll prove some theorems on that later on. But I guess an important notational point, and this is not just notation, this is actually an important physical quantity. We'll define now what's called the circulation. The circulation of a vector field F around a closed curve C. So this is important. C has to be a closed curve. So we define the circulation of a vector field F around a closed curve C as the following. We say it's the line integral over this closed curve, the circle here, the line integral over C of F dot t hat ds, or in our other notation, the line integral of f dot dr. And with our previous interpretation of this accumulation, it makes a lot of sense why this is called the circulation. It's kind of like, you know, this value, if you calculate it, gives you a direct measurement, right, of how much this vector field is rotating with this curve C, or tangent to this curve C. That's exactly what this integral is giving you a measurement of. This is kind of like a very special idea here, and it's going to lead to some very big things. One of the biggest things that I can say now is that we can actually get using this idea of circulation, we can redefine or get an alternate definition of curl. And we do that in the following way. So suppose we want to define the curl of a vector field at some point r using the idea of circulation. Right? How can we do this? And recall that the following: for a vector field f, the curl of the vector field f was defined relative to an axis n. Right? The way that we use this is we say that this, the curl of the vector field f, in the direction of n is the amount that f is rotating around the axis n, and this is definitely going to be measured at the point r. Right, so that's important to specify here that we're evaluating this at the point r. This is at the point r. And the way that we can do this in terms of the circulation is actually in terms of a limit. And it's a very intuitive idea, but it has very kind of deep connotations and deep reasons for working. So we say that the curl, and I'll avoid using the vector language. I said we don't want to. It is in fact equal to the curl or the cross product of that del operator with the vector field, but I want to avoid the way that we defined it earlier. So we'll just use the word curl, which I think is a nicer way in general anyway of writing down the curl of the vector field. So if this is an alternative definition, we can say that the curl of the vector field f in the direction of n hat is going to be defined as the limit as delta A goes to 0 of the circulation of the vector field around delta C of f dot dr, of the circulation of the vector field around delta C divided by delta A. It's the limit as this delta A goes to 0. So what is this exactly telling us? Well, it's saying the following. It's saying that if n is some direction, and the contour C is some contour, or the contour delta C is some contour that is progressively getting smaller and smaller and smaller, this is, say, delta C1, delta C2, delta C3, where the corresponding areas are getting smaller and smaller and smaller as well. At the limit of the in some sense the average circulation over the area delta A, this limit as delta A goes to 0 is the total curl, amount of curl at that point, the amount of rotation at that point. In this case, and this is right here the point R. So up here in this limit, delta C is a contour or a curve centered at R. Going around N. And A, or delta A, is the area of the surface bounded by delta C. So this is one way of, or a different way of defining the curl. And what's really nice here is that in some sense we can think of this for small values of delta A as like a measure of the average circulation of the vector field F on the curve delta C. And we're going to see that this definition of curl is perhaps actually better than the previous definition of curl, and more importantly, it's exactly equivalent to our previous differential definition of curl, as long as F is smooth enough. So this is perhaps a better definition for curl. And not only that, but it's exactly equivalent to the previous definition. And one of the reasons that it's so useful is it's a useful approximation tool. So for instance, for a small enough curve, so for a small enough curve, delta C, delta A also has to be small as well. We have here that the curl of the vector field F dot n at the point R is just approximately equal to, because that limits, the limit is delta A and delta C go to 0, but if they're small enough, then this value, the curl of F at a point, is going to be approximately equal to the circulation integral over delta c of f dot dr divided by delta a. Which means that for small enough delta A and delta C, the circulation around a curve is approximately equal to the curl at some point times the area of delta A, where delta A is the surface bounded by delta C. So this is a useful approximation very often if you want to, say, approximate a circulation, and will definitely be useful in your homework and the web work.